Bismillahirrahmanirrahim. Today, we'd like to start the new topic called multi-rate digital signal processing. So this multi-rate mentioned that we have not a single sampling frequency, we may have multiple sampling frequency. What is the purpose of multi-rate signal processing? That should be understood before starting the topic. For a practical purpose, if we have some processing unit, and inside that processing unit, we might have different units as well, where we are processing different sort of signals. For example, one unit is processing voice signal, one is voice signal that can be processing with a particular sampling frequency, F1. Like there is a video signal that is processing into F2. There might have the temperature or any other sensor signal that is processed with another sampling frequency, and there might be another signal which is also processing with another sampling frequency. So there might be a few number of sampling frequency. However, after having the sampling those things, after having some filtration and the processing, we might want to have our output as a single sampling frequency of F, which can be incorporated with other device. Okay, that is why there is a necessity to handle different sampling frequency F1, F2, F3, F4 to a certain fixed sampling frequency. Very practical examples will be given during this lecture. However, for a very quick understanding, let's say we process something with a very high sampling frequency for a particular purpose, very high sampling frequency FH, and now we want to reduce that sampling frequency, so we need a downsampling for that. And sometimes we process our signal with a very low sampling rate. We want to increase our sampling rate. This is called upsampling. So these two methods are necessary to change our original sampling frequency to another sampling frequency. Okay, so this is the whole objective of today's lecture, how to deal with this multiple sampling frequency. So in previous lectures, we have done the sampling with a single sampling frequency for a particular system. However, here we can use certain number of sampling frequency. We can use that. Okay, so to understand this whole process, or to primary operation in multi-rate processing are, there are two names we should remember. One is decimation and another is interpolation. Okay, so to perform the decimation, we need a downsampling plus some filtering. So what is a decimation? We'll explain within a few minutes. However, it actually needs, first of all, downsampling as well as some filtering operation. Similarly, in case of interpolation, we need upsampling as well as we need some filtering option. So combinedly, this filtering and the upsampling gives us this interpolation operation. Now, if we consider only the downsampling is not the decimation. Downsampling plus filtering is the decimation. upsampling plus the filtering is the interpolation. Whenever we talk about downsampling, this can be represented by this following equation or mathematical concept, where yn is equals to x twice n, where xn is your original signal, and it will be downsample with a factor 2. So we can write yn is equals to x twice n. In general, we can write x mn, where m is the downsampling factor. In a graphical representation, with help of graphical representation, we put it like this. M is the downsampling factor, and arrow shows the downsampling. So we have xn, and in the output we have yn, which is nothing but x m into n. That is the way we can show the downsampling process. We'll explain that definitely with frequency domain representation as well. In case of upsampling, it can be represented by this, the similar fashion, and the block diagram can represent like this, a up signal by this arrow, and sometimes L, or you can also mention it as M, where that is the upsampling factor. For example, this is your xn, and that this is your output, where output is equals to x2 divided by L, where L is the downsampling factor. So these are the two key processes for the multi-rate digital signal processing application. So we need to know about those two processes very deeply to understand the multi-rate signal processing. Decimation, or you can say downsampling, we'll describe in this subsequent section. So we can start with a very simple example. As we can find that we can start with a continuous signal. It is sampled with a sampling frequency fs, and we can define that sampling frequency, of course, and afterwards we find this kind of stem. Okay. So for example, if we took a analog frequency of 20 kilohertz and we have chosen the sampling frequency as 160 kilohertz, then the normalized frequency or relative frequency is equals to 20 divided by 160. That is 1 by 8. That is the normalized frequency. And this can be also mentioned as how many samples you have in a particular signals for a full cycle. So how many samples you have for a full cycle. So that means we have 8 samples for the full cycle. Let me check it here. We have 1, 2, 3, 4, 5, 6, 7, 8 samples. These 9 samples is basically belongs to the next cycle. So we have 8 samples where we cover a 1 full cycle. So if we put 2 divided by 8, it shows that it is equals to 1 by 4. That means we have 4 samples per cycle. So we have defined our F in that way. The cycles per samples. Or in other way, we have also can define in this way, F divided by Fs, where F is the actual frequency and Fs is the sampling frequency. So those are the very basic things. Okay, after doing the sampling of 160 kilohertz, or you can say for the relative frequency 1 by 8, we have found this kind of discrete signal. Now we need to do the downsampling with this equation. This is the definition of the downsampling. What does it mean? Let's say for y0, it will be x2 into 0. That means x0. So x0 will come to the y0 location. That means 0th sample will contain this sample. If we want to find y1, it will be x2 into 1, that is x2. So x2, which is this one, will move to this position. Similarly, if we try to find y2, that will be equals to 2 into 2, 4. So that means this one will move to this location. So if you continue, we can find that after each sample, there will be a cancellation of the samples. And afterwards, we got the following values, this one, this one, this one. And we can reconstruct our yn like this. Okay. And this is basically the downsampling in the time domain. So we have downsampled our signal with a factor of 2. This is the downsampling with a factor of 2. Now you can also downsample with factor of 3 or 4 or 5, whatever you want. Definitely you are missing some data. That is the limitation of the downsampling concept. However, that will definitely has some purposes. Okay. Now the question is, what about the frequency? From knowing the or understanding the time domain sequence, you can find this was the actual signal frequency. Now the frequency looks like this. So the frequency is increasing or decreasing. From this original signal, it looks like this after doing the downsampling. So the frequency is increasing or decreasing?
So increasing.
Definitely, it is increasing with a factor of 2. Let's say this frequency was in the analog domain, the frequency was like 2 hertz. Then of course this decreasing or increasing? The frequency is decreasing or increasing? That is increasing with a factor 2. Now this is 4 hertz. You can see from the time domain concept, if this t is 1 second previously, now of course this time is now 0.5 second. So within 1 second there is one period. Let's say this is 1 hertz, and within 0.5 second we have a single period. So that means this is 2 hertz. So frequency is increasing with a factor of m, where m is equals to 2. What we have done, we have xn downsampled, we have downsampled, and we have n. So after doing the downsampling, the frequency basically increased with a number of multiplications of the value of m. So what about the frequency of yn? Of course, it will increase with the factor of m. Let me show it in the frequency domain. We can also write in this way. What is the normalized frequency of this signal? Definitely we have found that this is 1/8. Now what is the normalized frequency of this one? Normalized frequency. How many samples we have in a cycle? 1, 2, 3, 4. for a unit circle 1. So this is now the new sampling frequency. So if we want to draw it here, let me draw it. The frequency domain perspective. Let's say this is half, and this is half. As you know that in the scale of small f, the range of the signal is from -half to +half. On that scale, you can find that this 1/8 is like, let's say this is 1/8. Let's say this is 1/8. 1 divided by 8, and there will be another stem. This is -1/8. For this one, 1/4, we can definitely write it at the middle of 0 to 1/2, and this is the value. So this number is 1/4, and this is -1/4. Of course, you can find that the frequency is increasing, and that can be represented in the frequency domain as well. So whenever you are doing downsampling, of course, the frequency will increase with the factor of the downsampling number. If you have any question during the lecture, just please raise your hand so that I can repeat the things if necessary. Okay, so we have already discussed this in the earlier figure, that previously we have 1/8, and due to the downsample with the factor 2, now the new frequency is 1 divided by 4. So of course the frequency is shifted due to the downsampling. This is with the scale of f, small f, and you can also write it with the scale of omega, with the relative frequency. Now, in the previous example, we have taken the case as the xn. Xn is a single frequency component, so that was 1/8 and shifted to 1 divided by 4. Now, if that is a band of signal, let's say from 0 to 20 kilohertz, 0 to 20 kilohertz, then what will happen? Of course, all the frequency will be shifted, and that can be represented like this. So before doing the downsampling, it might be looks like this, from 0 to 1/8. Okay, let's say it is like that. So we will start with 20 kilohertz is a single frequency, and the sampling frequency is 160 kilohertz. And due to that, we found 1/8. Now our frequency range is from 0 to 20 kilohertz. So that's why we find the full range from DC value to 1/8. So all the things are there. And also in the negative side due to the mathematical concept. Now, if that is downsampled with a factor m is equals to 2, but we found that the maximum value 1/8, it has been shifted to 1/4. That means this point is shifted to that point. So similarly, all the points are shifted. And now you can find the frequency band looks like this in the right side, positive side, as well as in the negative side. And it is very convenient to understand that all the points should definitely shifted or increase the value with the factor 2 or m. In general, what happens, okay, this is the overall diagram in the frequency domain. Before going to this part, we can understand this point. That means if we look at the half cycle, these are the points we are considering. And in that case, this is the time duration, the sampling time between two samples. From there, we can find the sampling frequency fs, which is equals to 1/t. However, whenever we are talking about downsampling, we are canceling this. We are canceling this. So whenever we are canceling this one, then what is the sampling time? Now the sampling time is this, which is, for this case, for a particular case, 2 into t, or you can say m into t, because m is the multiplying factor. So now the sampling time is increasing, increased one, and we can say that fs hat, it is equals to 1 divided by mt. So that is the sampling frequency. You can also put it in the capital fs, so you know that what we are mentioning here. Now if we go for small f, in the previous case, that is f divided by fs. Okay, and in that case, what we have found, f will remain constant because that is the frequency, and comparing to that, the new frequency, the sampling, the relative frequency is now f divided by fs hat, where fs hat can be written as fs divided by m. Fs divided by m. So we can write in this way, m into f divided by fs. Okay, just putting that value. So what we have found here, what is this? This is nothing but our previous sampling frequency. So what we can say, the relative frequency, new relative frequency, is equals to the m times of the previous relative frequency. As we have already developed that, the previous relative frequency, if that is 1 by 8 and the factor m is equals to 2, in that case the new relative frequency is equals to 1 by 8 into 2, which is 1 divided by 4. We have already mentioned it. So we can also mention it like this, and it has been discussed here. Okay, so now we can move to the frequency domain representation. So in general, whenever the t is equals to t, that means the time frame is t, then we can understand what is our sampling frequency. Always we are writing the sampling frequency is equals to twice pi f. Okay, so that's why this is twice pi divided by t, and it can be plotted like this. Let's say our maximum frequency is omega 0 in the capital form. Now if we look at to the frequency domain, in the relative frequency domain, that means in the discrete domain, this is in the continuous domain and this is in the discrete domain. So what happens, it will be divided, this will be divided by your sampling frequency omega s. So we can take capital Fs or omega ss, Fs, those are the same. Okay, so different notation, but those are the same. So if I look into this, what is this? We are mentioning in a way, this is omega 1, which is nothing but twice pi into small f1. So omega 1 is equals to twice pi small f1. Now twice pi small f1 is what? The particular analog frequency, which is omega 0, divided by, so let's say we can put f0. Okay, that will be more logical. Omega 0, the natural frequency, divided by omega s, the sampling frequency. That's what we are mentioning at that point. Okay, and of course this is pi, which actually been mentioned as in the scale of f, this is half. That is the maximum range. As we already know that in the omega scale, the range of vision or range of view is from minus pi to plus pi. Okay, and then we have the replica. Okay, so you can describe the replication. And now if the sampling time is now empty, not necessary we are first sampling it with the t and then we cancel the sample. Rather, we can go directly with empty time. So that means we have the signal like this, and we can choose this time value twice t, and we sample it like this. So we are taking this, and this. Previously, we have taken some other sample in between, but now we are neglecting those things directly. So now we have this sample, and this sample, something like this. In that case, what is the sampling frequency? Of course, this is the sampling frequency, the new sampling frequency, omega s is equals to omega s divided by m. We have shown it. And according to that, this is the actual value. And now it has been shifted. This frequency is now shifted to the value of omega 0 m. This is not at this point. We are mentioning what is the frequency, how the frequency looks like. The frequency looks like omega 0 into m in case of in the relative frequency. Because what is the relative frequency at this moment? If I put it there, the relative frequency, new relative frequency omega 0 is equals to definitely twice pi f0. What is the f0 now? Twice pi. F0 is new the actual frequency omega 0. Of course, omega 0 is the actual frequency divided by omega s hat. What is omega s hat? We already know that this is omega s by m. So we can write twice pi omega 0 divided by omega s into m. And we can again write twice pi. This is nothing but the value small f 0 into m. Now this term, we already know that this term is supposed to be this one, and now that is multiplied with the value of m. So we are proving that, of course, this point is now in the relative domain, the frequency is now increased with the factor of m. So don't confuse with this term. This term just shows that it looks like the original frequency is now multiplied with the m, and actually the frequency is definitely increased with a factor of m due to the downsampling. Okay, I have already mentioned that the decimation and the downsampling are not the same, but the downsampling is a part of the decimation. So before the downsampling, we need to put a low pass filter to pre-process our signal. Otherwise, that makes a big problem, which can be known as aliasing of the signal. Due to the aliasing, that problem actually been occurred. So in the flow diagram, what we are mentioning, so first we need to take our signal xn, original signal, need to be passed through a low pass filter, and we found a signal after passing through the low pass filter, and after that we are discarding those values. How we got this xn? So we have our xt, we put analog to digital converter where the sampling frequency or the sampling time is t, and we got our value xn. Now it's gone through a low pass filter. It can be gone through a low pass filter, and then it's given to the yn. Or in other way, what we can say, we can take an xt in this format, forget about this xn, and then we got this yn. Always we are putting this low pass filter, and after that we are discarding the value, and at the end we are getting our final output. Now, why we should put this low pass filter? We have discussed it in the basic function of basic lectures when we have discussed on the aliasing. However, this could be not redundant to explain here again. Let's say we have a signal like this, okay, and inside this signal we have the basic signal as well as it is incorporated with some noise. Okay, it is incorporated with some noise, and always we have this kind of possibilities that noise is there, and this noise it can be in different fashion, and this noise can be incorporated due to the sampling as well. In many cases, due to the sampling, it can be also implemented. Okay, so what we can do here, this is a very practical example. Let's say that the frequency domain behavior of a signal, let's say for in case of xn, the behavior is like this. Up to this, we have the signal which is necessary, and after that we have a tail, and it is up to pi, and that actually showing the noise. Don't confuse with the things we are mentioning whenever we are converting our analog signal to the digital signal. In case of analog signal to digital signal, we always put a low pass filter. Okay, so the principle is same, but the purpose is different. So here we have the original signal, and also that has been incorporated with the noise, and of course that is true for the other parts because that is the replica. Now the thing is, if we do the upsampling, so here I'm just intentionally put the factor m, but you can put any factor. Now, if you put the factor m here, if you took the factor m for downsampling, what happens? This pi by m frequency will be shifted to where? Pi by m into m, so which is pi. That means if I show it here, so this is pi, this is pi. Let me erase these things. So my signal maybe like this. This is pi by m divided by m. Of course, you have the same thing there, minus pi by m, and we have the noise the both side. Okay, now due to upsampling, now the signal can be gone up to this, because as you know that we have found pi by m into m, so that is up to pi. So now this point is shifted to this point, and similarly to this point. What about this noise? Of course, this noise part is also shifting like this. And due to this noise, what happens, if we consider this is the point of twice pi, we can understand easily that if I make a line over there, the main signal strength will come up to this, or I should take another color. Okay, the signal will come up to this, and that will be like this. Okay, so take it like a continuous format. So this is the original signal, and you will find the replica of this. But what about this noise part? This noise part, previously, this is the noise part. It will be extended due to this factor of m. And now it will be folded back to your original signal. So it will be folded back to your original signal. So as you can find that, this is your original signal and this is the noise. So now you can see that the overall this whole part will convert it to an alias signal. So you are missing your original signal completely. So that is why it is always better that we need to put a filter like this so that we can cancel the noise before giving this signal xn to a downsampler, because downsampler will just downsample it and increase the frequency, and due to increasing the frequency, the noise frequency will also increase, and that gives the aliasing effect to our original signal. That is why this is always important to put a filter, low pass filter, before giving it to the downsampler. And how to select this bandwidth of the filter, it definitely depends on the purpose, up to which frequency you want to cut down, you want to carry through for your calculation. That depends on the purpose. There is no hard and fast rule where you need to cut the thing. Okay, so you can choose yourself. You need to understand which part is important for your signal processing. So whenever we have put in this kind of filter with our original signal, then we got only this part without the noise. And then after that, we can implement our downsampling over our original signal, the filtered signal, and then we can find the things like this. And there is no aliasing effect. Okay, so this is twice pi, so we don't have any overlap between our signal. So how to choose? Again, the concept is how to choose the value of m. What could be the maximum value of m? So let's say this frequency, I'm putting this frequency value is f. So whenever you are multiplying f with m, this m actually came from the multiplying factor of the downsampler. What could be the maximum value of this f into m? What could be the maximum value of f into m? Any of you? You have your original frequency, maximum value of the original frequency, let's say f max. Now, whenever you downsample it, it will be multiplied with m. Now, what could be the value of this frequency in the relative frequency domain? It could be the maximum, it would be pi, because that is our range. So that is how you can find what should be the value of m. You need to choose the value in such a way so that the f, I should write small f relative frequency into m, that should be less than equals to pi. Otherwise, still, even though you are canceling this noise, even though you have the aliasing. For example, if I choose the value of m in such a way that it will exceed the value of pi, of course, due to this crossing, we have the aliasing effect definitely from the other part of the signal. We have discussed this during the aliasing effect explanation. I believe up to now this is very clear to you. So what is the purpose of the low pass filter? We have already discussed. Okay, now step by step, this is how it actually been happened. So I have already mentioned that we have xt, we need a low pass filter here, low pass filter, and after that we got xn. This low pass filter, purpose of the low pass filter and the purpose of the low pass filter is completely different. Okay, so this is the second low pass filter. If we want to go for the decimation, Otherwise, we do not need this filter. Okay. So let's say this is a practical example. Let's say this is our xn. And as you can see that how the xn looks like. This one, this is the xn. And as you can find that, how come this filter noise, this noise actually been incorporated? I have mentioned this noise pi. I have incorporated the minus pi. How this noise actually been found? Whenever in the discrete signal, the sudden change of the signals been happen, sudden changes. Okay, it might, you can understand. I have put it some dot. If the signal looks like this, it is very smooth. This is for example. Okay, this is for example. If it is like that, in that case, the frequency component may be restricted up to this. But if the signal point contains like this sharp jump, in that case, it actually incorporate some noises. As you know that the sharp rising or sharp falling gives phenomena, and there is some shaking of the signal. Okay, so due to that, there are some extra noise inside the signal. Now what we can do, we can implement some filter. And what does it do? You can find that it decrease this value, it decrease this value, this decrease some value, this will increase some value, decrease some value, increase some value, decrease some value, and ultimately it gives some smooth function to the output. Of course, you can understand we are missing some data. However, we can also avoid the fact of the aliasing. That is our advantage. You need a trade-off. If you don't, if you think that okay, I don't go for this low pass filter, okay, you can do that. But of course, there is a aliasing, and it will destroy your original signal. Rather, we can go through a low pass filter so that the signal is smooth than the previous one. Previously, the signal was like this. You can see it is zigzag, and of course, there is a very high frequency component. And now the signal, you can see that this is smoother than the previous one. Of course, this is just an hypothetical example. Okay, so by this you can understand the signal is now passed through a low pass filter, and it cancel out at the high frequency. And now after doing this, we are now ready to cancel some intermediate signals, and after that we got our expected yn, which is downsampled by the factor of 2. So 0, 2, 4, 6, 8, 10, and the other sample will cancel. It has been discussed elaborately in this lecture. I believe you understand the purpose of this low pass filter. Don't confuse with the low pass filter after XT, low pass filter. This also been used to reduce the or control the aliasing from the original signal, because the original signal may have some noises. You need to cancel that. Again, whenever you are doing some processing of this kind of things, that means you are suddenly increase the frequency. You had some target, suddenly you are increasing the frequency with a multiplication of 2, 3, 4, 5. So huge expansion of the frequency. So now you again need to put a low pass filter before that. There's a practical use. So always example says many things. So practical use of downsampling, such a such a processing required may arise. For example, when a speech signal is oversampled at fs 32 kilohertz. So it is oversampled. Why it is oversampled? Okay, maybe for a particular purpose. Let's say you want to store the song in a way so that it's very, very sound to you. However, whenever you have a lot of data, you want to process something, then you want to go back to the downsampling. For example, if you want to upload some picture to the YouTube, picture to the Facebook, or video to the YouTube, then what it actually do? It actually downsampled your data. So that means you have recorded your signal, voice signal, with a high frequency, high sampling frequency. However, the system will not permit all the signals. So then it will be downsampled. That is also a practical case. Okay, now come to this point. Since we are interested only in a band of 0 to 4 kilohertz, sampling rate can be reduced to 8 kilohertz. We know that. We know about the Nyquist theorem. So it is a sample with the sampling frequency is equals to, I should write capital letter. So for the convenience, this is sample with 32 kilohertz. Now what we are trying to do, we need to reduce the sampling frequency to 8 kilohertz. How to reduce that, and what would be the limit? So you should have the knowledge. So we already know that our voice signal actually been content with the value 0 to 4 kilohertz. So we can go up to 8 kilohertz. Less than 8 kilohertz, definitely it will give the aliasing effect to your voice. So what we can do, we have this CD, which is burned with the sampling frequency 32 kilohertz. Then what is the first step? We need to go for the low pass filter. We know that where is our necessity. So that is the band 0 to 4 kilohertz. That is the filter. So 0 to 4 kilohertz. And then we got our signal to perform the downsampling. What would be the factor? We got this factor very easily. So from 32, we need to move to 8. So we can find that 8 into m, it should be 32. Of course, that is the new sampling frequency. So new sampling frequency is that. So we know that the value of m is 32 divided by 8. So that is 4. So we understand how we can got this value of the 4. We made the relation between the sampling frequency, previous sampling frequency, and the new sampling frequency. If you can look at the previous section, we can find it. Yeah. So this is the basis of the two sampling frequency. Okay. So this is how you can change the sampling frequency. This is example of multi-rate signal process. Okay, which kind of a low pass filter you can implement here? Okay, we are talking about this low pass filter. So there are IIR type filter and FIR type filter. Okay, the thing is, in case of IIR type filter, as you know that for this kind of filter, we need to wait for finding all the sequences of YN, because you know that in case of IIR type filter, there is a feedback process. So whenever you have the feedback process, then let's say this is WN, and this is your XN. If you want to go to the next step, before going to the next step, you need to calculate all the samples YN, because all the samples of YN is also depends on the sequence of XN. So it is not real time in that case. So you need to wait after having all the calculations of YN, then only you can proceed to the next step. And that is why IIR low pass filter is not being used for this decimation. Always we are using the FIR filter. Again, we know that we have some advantage of the FIR filter, which is which is linear phase, and the group delay, which actually leading to the group delay is being constant. So that's why this is very popular. So we always use the FIR type low pass filter for this decimation. So it has been discussed here in this note as well. Okay, so FIR filter is our choice. Now the second term is the interpolation. This is pretty much easy, straightforward. This is again known as the upsampling with some filtering is the interpolations. Okay, the concept is very easy, straightforward. We have xn. From xt, we have xn with a sampling frequency. And whenever we have yn is equals to xn by 2, what happens? Let's take y0 is equals to x0 by 2, which is x0. So directly we got this sample. If we target yn, what is that? X1 by 2. So x 0.5. Do you have any value at x 0.5? No. And that's why we are planting a 0 there at the location of 1. Now, if we target y2, that is x2 by 2, that is equals to x1. So x1 will come to that point. Similarly, after each and every points of the xn, we are planting a 0, extra 0 all the way. This one is actually the original 0. So before that, okay, I missed 1 point, so there should be another 0 here. Okay, so for this practical 0, there is a 0, then value 0, value 0, value 0. This is a value, and then we should have a 0, then value 0, value 0, value 0, and so on. So we are implementing some extra point. And now what we can understand, previously the signal was like this, and now the signal is spreaded. Okay. Now, what about the frequency? If this is 1 hertz, now this is, okay, let's say this is 2 hertz, now this is 1 hertz. So that means the frequency is now reduced with a factor of the interpolations factor. Okay, so we can write in this way. Xn we have shown in this way, the downsample of the value of L, and this is of yn, where yn is equals to x L divided by n divided by L. So how the frequency will change is definitely with the factor of L. So you need to decrease the frequency. So if this is 20 kilohertz, now it will be with the factor of 2, that is 20 divided by 2 kilohertz. So 10 kilohertz, it will be reduced to the value. But there is a problem, still there is a problem. If you try to, how you can say that the signal will follow like this? It is not true. It will basically follow like that. And then it looks like more higher frequency component actually been introduced. This is a problem. This is a problem. And that is why we need to put a low pass filter so that we can get this kind of signal output. Okay, I have shown it in the next page. So first of all, the frequency representation. Please go through this and you will find it very convenient. So previously it is like omega 0. We have chosen that frequency is equals to pi in the relative frequency. Now omega 0 is shifted. Omega 0 will remain omega 0. Okay, omega 0 is the original frequency. What actually been shifted? The shifting is the relative frequency. The relative frequency is shifted. So previously that was the location at that was pi. Now it is shifted by pi by n. So downsampling makes the frequency, let's say any frequency, any relative frequency f1 multiplied with m, And upsampling make any frequency divided by m. So we have already shown it by this practical diagram. So always remember this practical diagram. Of course, the frequency is reduced. And then it will be very easy to understand in the frequency domain. Okay, so there is a mistake in this diagram. So you'll find it in the next page. What is the mistake? Okay, whenever this thing is now reduced to this thing is reduced to this thing is not correct. Okay, so what will be? So I'll show it in a minute. Okay. Okay, this is the whole process. Try to understand. This is very simple, easy, and important. Okay, so this is your xn. You can follow. And then we are inserting the zeros in between, and this is that value. This is a some kind of electronics by which you can do that very easily. And now what we need to do, we need to, this is xzn should be processed through a low pass filter. What the low pass filter do? It will stay, it will take the previous sample continuous for a period of time by the RC circuit. So the sudden change, okay, so from there, okay, it should goes like this. Okay, no, we don't like this path. We should follow this path. So how we can manage this? Okay, so this is the way. So by passing through a low pass filter, we now get this kind of signal. You can follow very easily that previously the signal looks like this, a zigzag. Now it has been converted to a smooth signal, and which is very close to the format of your original signal. This is your original signal format, which is a format of your original signal, this one and this one. So this is the beauty to use the low pass filter. Again, what should be the band of the low pass filter? Definitely you need to understand from the purpose. Okay. Now this is the place where I have corrected the mistake. So there is a mistake here. So I'll say where is, you definitely understand where is the mistake. So now try to understand here. This is our original baseband. And now you can understand this point will be shifted to this point, okay? Pi by m with the factor. Now, if we think about this point, where it will be shifted, definitely twice pi will be shifted to twice pi divided by m, isn't it? So that's why this point, let's say point number A, this is the point number A, and it will be located at twice pi by m. So of course, this point will be shifted to this point. So that means this whole bunch of thing will be shifted to the left. And that is the mistake I have made. That means this will be basically shifted to the left. Definitely the other branches, all the branches will be shifted to the left. And that's why you can find this kind of phenomenon. Of course, this is a continuous one. It is just going on like that. Okay. So what is our range of view? Our range of view is from, let's say, from pi, minus pi to plus pi. Now, what we can see, we have some extra signal there. We have some extra signal there. And we don't like that. What we like within this pi, we just need this lobe. We don't like this. We don't like this. And that is why we need to introduce a low pass filter here in such a way that we only can get the signal of minus pi by m to pi by m and reject all other signals from this new frequency domain. As you can understand, the frequency is reduced. This point is now reduced to pi by m. That is fine. However, this point is now also coming to this, and that's why there is another lobe inside the pi. It might be a number of lobe depending on the value of the capital M, the downsampling factor. Sometimes we are using L or sometimes we are using M, so all the same. I believe you understand the problem and how to solve that problem. The solution is very simple. We need to put a low pass filter so that the extra signals will gone through. Okay, and this is what we have done. We have our signal, we have put at the zeros. Now if we add those things, that means you are also incorporating the higher frequency. Rather, we are putting it through the low pass filter so that we can get a very smooth signal output, which is like this. Okay, we want this and we got this by putting the low pass filter. So we need to be very careful about choosing the bandwidth of this low pass filter. And after that, we got this kind of signals where, let's say, this is the location of pi. So now we are in a safe mode. So we don't have anything inside minus pi to plus pi without our own signal. Okay, so we are happy with this. Okay, now the thing is sampling rate conversion by non-integer factor. So in the previous case, what we have done, if we have 32 kilohertz sampling frequency, we are down sampling with a factor 4 and find the new sampling frequency is 8 kilohertz. We happy with that. But now what we are planning, let's say we start with 32, but we want to convert it to 8.1 kilohertz. How we can do that? So when there is a non-integer factor, so previously the factor was 4, which is an integer factor. Now if we want to make this factor 8.1 divided by 32, definitely that is a non-integer factor. So this is an example where we have a digital audio tape of 48 kilohertz. So an example is transferring data from the compact disc system at a rate of 44.1 kilohertz to a digital audio tape of 48. So what we are planning, we have the signal 44.1 kilohertz sampling frequency. We want to convert it to the higher frequency. Why this is necessary? Because the DAT, that means digital audio tape, is compatible with 48. You don't have anything to do. If you want to take your signal from the compact disc to the digital audio tape, you need to upsample the things. You have to, because that is based on the compatibility of the system. Okay, it needs to be improved from 44.1 to 48. So how we can do that? The task is very simple. This is a non-linear, of course. Now how we can solve it? The concept is, first of all, the concept is from 44.1, we need to, let's say, we need to upsample our things with a sampling frequency, let's say x, and from the x we need to downsample it to our targeted sampling frequency 48. So that is the process. That means 41.1 to upsample it to some point, not to the 48, in such a way so that we can take an integer at the upsampler like m, and whenever we are, so this is an integer, and whenever from the x to 48 we are again utilize an integer l as a downsampler. So this is for the upsampler and this is for the downsampler, or vice versa, whenever we are doing the upsampler l and the downsampler m. So whatever the things. So that is the concept, and how we can do that. The thing is simple. 48 by 44.1. we are multiplying the both side with a 1000, or you can say 100, whatever. So we want to undertake this one, and we need to find this ratio 160 over 147. Now what we need to do, by this term you can understand the 44.1, this signal should be upsampled first with this factor. This should be upsampled with this factor, and whatever you have found, that is x, and then you will downsample with this factor, and eventually you got 48 kilohertz. Okay, so that is the process. So the thing is pretty simple. Here is given this example. So you can start with 41 kilohertz, upsample it, then downsample it 47, then you can come to the 48 kilohertz, and that is the way how you can tackle this non-integer ratio. Okay, therefore we upsample it by 160 and downsample it by 147, and that will achieve the things. Okay, and in diagram we can show that this is our signal. The frequency was 44.1, then of course upsample it with 160, and what is the frequency? Definitely we know that what is the sampling frequency. Since we are upsampled, the sampling frequency is increased here, and we need that low pass filter. You know that why we need that low pass filter. Again, this is the input of the decimator. We need the low pass filter, and then we downsample it 147, and after that what we got here, this is 44.1, and this is what, 44.1 into 160. You understand, this is again 44.1 into 160, 44.1 into 160, and what about this? It will be divided by m. So 44.1 into 160 divided by m, 147, and that will give 48 kilohertz, and that is how we can find. Two important things I can discuss here. We have 5 minutes. One is, can you do the opposite? First we can go for downsampling and then for the upsampling. Can we do that? Yes or no? Because the ratio actually gives the same result. The ratio will give the same result. However, it is not intelligent to do that, because if we go first downsampling, you are missing some data from the original signal. That is why it is always preferable that go for the upsampling first. Upsampling means you are interpolating, so you are giving some more data inside, and after that you can go for the downsampling. So never go for the downsampling first, rather go upsampling first. The second thing is, you can find that there is one low pass filter, another low pass filter, and they are cascaded with each other. So now if we look at this section closely, we'll find this, and let's say the bandwidth of this low pass filter is 0 to 4 kilohertz, and the bandwidth of this low pass filter is 0 to 2 kilohertz. So combinedly, what should be the bandwidth of this filter? What should be the bandwidth of this whole compartment? Any of you? The bandwidth of this whole compartment should be 0 to 2 kilohertz, isn't it? Because it is worthless to use 0 to 4 kilohertz here, because ultimately it will be reduced with the 2 kilohertz just after this process. and nothing else. You are not doing anything. So that's why what is the minimum? Here we are mentioning the minimum of the band, minimum of, so it mentioning the maximum. So this is literally pi by L doesn't mean any value. It means that the prominent signal, this is pi and this is pi by L, let's say. This is the prominent maximum signal you need. So depending on the prominent maximum signal you need, and the lower value of that is the bandwidth, of the these cascading low pass filters. Okay, so this is how you can calculate your low pass filter from the purpose. This is an example. You can do it. All the values are given. Fs is 8 kilohertz. We need to convert it to the 20 kilohertz. Okay, so what could be the value of L and what could be the value of M? You can decide, and what could be the bandwidth of the low pass filter. Okay, one very practical things I can just illustrate, and this is the last topic. Illustration of the interpolation by a factor 3 by 2. 3 by 2 means 1.5. So that is a fraction. So let me introduce it with a very practical example. Here we have the xn, arbitrarily xn. So we have these samples. Now with a 3 upsampling value, we are taking L is equals to 3. That means we are introducing 2 samples in between. So what happens after passing it through a low pass filter? Of course, a low pass filter, what we have found this kind of signal. Okay, so this is the result after doing the upsampling. What is the factor? Remember, this was 3. L is equals to 3. Now what we can do, we can go for the downsampling of factor 2. Downsampling with a factor 2. So if we can come from this to this, downsampling means you are neglecting this one, and ultimately we got these values. What is this? Now, after having this downsampling, what is the frequency with respect to the original frequency? Previously, actual one is Fs multiplied with L, because this is upsampling, and you downsampling with the value of M. So that is Fs into 3 by 2. So that is 1.5 Fs. So that is a fractional thing. So how it actually been done in practice in case of fractional changes of the frequency. So this is all about the multi-rate signal processing. You can implement it in the practical domain for your practical purpose. So thank you very much for your patience and participation. Assalamu alaikum.